The simulation models passive underwater positioning, demonstrating how a vessel resolves its coordinates by measuring the time difference of arrival, TDOA, of acoustic signals from multiple synchronized coastal stations to map intersecting hyperbolic lines of position, LOP. This navigation framework is governed by both geometric layout constraints and dynamic fluid physics, geometric dilution of precision, GDOP, and vertical sound velocity refraction. GDOP dictates that positioning accuracy degrades when the angular arrangement of the baseline tracking stations relative to the vessel results in shallow intersection vectors, expanding the boundary of geographical uncertainty. Simultaneously, changes in ocean temperature, salinity, and hydrostatic pressure continuously alter the medium density, dynamically shifting the local speed of sound according to the Mackenzie formulation. This vertical velocity gradient forces acoustic ray paths to bend away from high-velocity zones and toward lower velocity layers via Snell's law, visually bending the navigational curves and introducing tracking variance between the vessel's true trajectory and its calculated acoustic fix.